So I think why don't we at least go ahead and I'll start an introduction for Longzhu. We're really happy to have Longzhu here from MIT. He's an assistant professor there now, and so originally he was an undergraduate at Tsinghua University. Then he was a graduate student with Feng Wang at Berkeley, doing several really beautiful experiments, including direct imaging of ABEVA domain walls with near-field optical microscopy in bilayer graphene. He went on to do really a number of beautiful works in various graphene multilayers, from bilayers to ABC trilayers with and without alignment to hexagonal boron nitride. He was a Kavli postdoctoral fellow at Cornell for a few years up through 2018, and has been at MIT basically since then, since 2019. So again, he's done some really beautiful work on multilayer graphene, and I guess we will hear about some of the most recent results out of his lab, presumably from multiferroic behavior all the way through fractional quantum anomalous Hall physics. So welcome, Longzhu. Look forward to it.
Okay, thanks, Ben. Okay, I think I should remember to turn this on. It's green now. Okay, thanks. It's very nice to be here, and thanks for inviting me, and I hope to see Zach tomorrow. So I'm going to tell you about experiment that we did recently, recent couple of years in crystalline multilayer graphene. Okay, so just think of this as part of graphite. Nature does a job for us, and we just need to isolate a certain part of it to reveal emergent quantum phenomena. Okay, there's no twist angle between layers of graphene. So before I get started, I'd like to thank all the people who contribute to the experiment I'm going to tell you. These are my group at MIT, especially the work I'm going to show you today are mostly done by postdoc Zhengguang Lu and a graduate student, very capable, Tonghang Han. And we got the nice HBM crystals like everybody does from Japan. And we got support from our theory friends at MIT and UT Dallas. And if you look at my website, you may get the impression that I'm an optics guy, and I'm still an optics guy, not as much as before. But when we start to think of ideas in this material system, we were actually not even equipped with the right thing to do it. So I had the fortune to get help from Hong Kong Park at Harvard to allow me to get into his stillfish to collect some of the early data. Okay. So we're condensed matter physicists, right? And the most interesting thing that we now ask ourselves is like, given these elementary particles that is there, what happens when you put them together in certain structures like a crystal? There are astronomical number of particles involved, and they are full of defects and disorders in any material that you can possibly assemble. But there have been phenomena that's really amazing that you can observe macroscopically and super robust, and tell you there's some guiding principles or important principle that you need to learn from condensed matter physics, right? So one of them, I use superconductivity as an example to show like when electrons are talking to each other, amazing things could happen. You can get Cooper pairs and become super robust against scattering. You get zero resistance, where it's quantized that way. And the other group of phenomena that I call topology is when you have some like non-zero numbers multiply some fundamental physical constant, and you can experimentally measure it. For example, the integer quantum Hall effect that you just pass a current in the longitudinal direction, you subject it to an outer plane magnetic field, and then you get quantize the value of the transverse voltage that is proportional to this Hall resistance determined by h over e squared, and an integer n here. Okay, so this n is later known as a Chern number. It's an integer, it's precisely quantized. Let's tell you there are different topology of different states here. So after this many years of condensed matter research, we have some lore about where to get these kind of amazing phenomena emerging from the assembly of these elementary particles. And we sort of learn one thing is that usually if you have a flat electronic band where the kinetic energy of electrons are quenched, the interaction between them start to become important, right? So we sort of know you want to look for flat band and large density states. On the other hand, in order to get topology, well, this is just my way of viewing it, this very basic concept of barrier curvature that you can get from, even like 1950s, tell you that you can have anomalous velocity of electron wave packet, and if you integrate this barrier curvature, you can get the Chern number that give you the topology in the quantum Hall state. And this barrier curvature is also some good starting point if you want to look for topological state of matter. Okay, so these are some very general lore, and it has been question for experimentalists like what material do you get to show to have this ingredient and possibly show the emergent phenomena. And we know that you can grow crystals, okay? We rely on the chemistry, the chemical bonding between atoms to form crystal that may give you a flat band, a barrier curvature. That's one way of getting such kind of phenomena. And sometimes you can grow like, for example, MBE, grown layer materials in the vertical direction, and you can subject it to high magnetic field. You can quench kinetic energy that way, and you get correlation topology. In recent years, we got another opportunities because these materials can be thinned down to the atomic layers, and you can reassemble them back into some heterostructure that was not allowed to exist in nature, by default. But you can sort of choose what ingredient to put together. You can choose a species of 2D materials. You can choose how many layers to put together. And you can choose how to put them together by introducing some structural change by, like, say, twisting them. And you are still in the two-dimensional limit, which means you can use gate electric field to control the charge density and the electric field independently. And especially since 2018, we have seen many work making use of this concept, so-called Moiré superlattice, that forms between two layers of 2D materials. And that adds even more flavor to this platform for studying correlation topology. So the general idea of Moiré is that you have two layers of material has the same lattice structure, but they could be exactly the same, or they could have a slight lattice mismatch. In the most general setting, for example, if you have graphene and HBN, they have about 2% lattice mismatch, which means you put them on top of each other at a 0-degree twisting angle, you already get a spatial beating on the order of 15 nanometers, and that is a so-called Moiré superlattice. And that additional modulation in real space can give you additional knob to control the bandwidth to get flat band, and also control how strongly the electrons are talking to each other in the flat band. And of course, you can also introduce the twist angle between these two layers to further control the periodicity of the Moiré superlattice, right? And you can generalize this Moiré superlattice concept to other 2D materials. For example, the very first one, even simpler one, is graphene on graphene. They are exactly the same, so the periodicity is completely determined by the twist angle. And this is where my colleague Pablo found superconductivity that really looks like, at least phase space, like a cuprate superconductivity. And there has been other Moiré superlattice materials people use to get correlation topological phenomena. For example, ABC trilayer graphene, HBN Moiré. This was done by my advisor Fei Wang together with David Goldhaber-Gordon here. And there has been like twisted TMD Moirés, and there are a lot of ongoing beautiful efforts on campus here. So we sort of have this old lore of where to get correlation topology, and we have this new approach of using Moiré superlattice of 2D materials. When I started my job at MIT, I was asking myself, like, what should I do? And now it becomes sort of clear that I should take advantage of both of them. In the conventional materials that in the crystalline form, you have this very reliable chemistry that can give you highly ordered crystals, very robust. But it has drawback of being hard to tune, right? You have the crystal grown there, that's all what you have. You can cool down, warm up, raise the magnetic field, but there's hardly more things you can do in situ there or structurally engineering it. Well, this 2D stacks heterostructures, you have much more flexibilities in assembling the structure and subsequently control the properties. But sometimes it's a bit annoying in the sense of homogeneity, because when you put two layers on top of each other, give it a twist, well, strain can easily change the periodicity, give you spatial inhomogeneity. That's not as robust as crystals, okay? So what I want to do is to take advantage of these two systems and find some, starting from some crystalline 2D materials that take advantage here, oops, and then add more flavors to it by neighboring it with other features, for example, Moiré. And, to reach a condition where, get a flat band, so I can possibly get correlation and topology, okay? So this is a general idea. And the question is, what crystalline 2D material am I going to use? The answer is graphene. Okay, you may get confused. Monolayer graphene has this linear dual cone, has one of the largest Fermi velocity. It just doesn't look like a flat band at all. Well, the thing is, you have to go beyond the monolayer. You go to several layers of graphene into a certain stacking order. And then I'm going to add flavor step by step to this core material called Rhombohedral multilayer graphene, and to show you more interesting phenomena. Okay, so here is an optical image of a tape exfoliated graphene. And obviously there are regions with different contrast, and in the visible light illumination you can build a direct correlation between the contrast with the substrate and the number of layers. Okay, if you measure the optical contrast, it takes discrete values that tell you how thick it is. Well, in fact, graphene or graphite is even more rich than just having different layer numbers, because there's no chemical bonding between layers. When you put them on top of each other and start to increase the layer number, there are different ways of forming multilayer graphene or graphite. And there are two leading stacking orders that people talk about all the time. One is called the Bernal stacking, or in another word, ABA stacking. So it takes this A, B, A, B, A, B positions as you stack up, and this is the most stable form of graphite. There's another stacking order known as rhombohedral graphene, or known as ABC graphene, right? This is actually Tony's paper that, he showed us ABC is like you stack layers on top of the existing layers and you keep shifting in the same direction. So this sequence of ABC, ABC just keeps shifting in the same direction. This is a metastable form of graphite, but it is still there. About 10% of graphite is in the rhombohedral stacking order. So I'm going to tell you that this rhombohedral stacked graphene is actually very, very interesting, but hasn't really been carefully studied. It's very interesting because it has a funny energy dispersion relation, okay? I'm taking two atoms or one unit cell from each layer, and the ABC stacking order, they just form this kind of staircase structure. And if I ask how does the band structure of rhombohedral graphene look like, all what matters for low energy is the electron coming from this A1 orbit and this Bn orbital, because all other things in between strongly hybridize and push themselves away from zero energy. This interlayer hopping energy here is on the order of 400 MeV, which means if we're only interested in something happens on the order of tens of MeV or less than that, we only need to consider the wave function at this orbit and this orbit. And because these two electrons are talking very indirectly to each other, you get this funny dispersion relation where energy is roughly proportional to momentum to the nth order. If n equals 1, you get a linear band, and if you start to increase the n, you get more and more flat band at small k, or low energy. Okay? And then if you get to something like 4 layer or 5 layer, it looks like, well, here's somewhat flat band. Okay? So this structure itself has some flat band in it. I would call it as a pristine flat band when you go beyond 3 layers. And it has another interesting property that these two orbitals are located at opposite layers, which means you can easily use a gated electric field to break their symmetry and further tune the band gap by opening up a gap that corresponds to the electrostatic potential difference between the two layers. So in this case, you can open up the gap, and what that does to the band is that it further squeezes the bottom of the band and even increase the density of states to give you, huge density of states. And I'll call this as kind of like gate-induced flat band. Okay? So I hope this convinces you that if you manage to stabilize this stacking order, you will have a chance to get, flat band. Well, the other ingredient that we sort of need is topology. And this is, rhombohedral graphene is also a good place to look for topology because the band crossing point, the direct points, are kind of topological object. There's, for 5-layer graphene, there's a barrier phase equals 5 pi per valley per spin. It's just 5 times bigger than what you get from monolayer graphene. At 0 gated electric field means the pristine form of graphene. You have this band crossing point, kind of like a singularity of barrier curvature. Well, when you open up the band gap, you can actually redistribute the barrier curvature to states near the band gap, right? There are K and K prime valleys in graphene. And if you just look at a fixed gated electric field, the two valleys are always time reversal pairs of each other. Their barrier curvature for the same band are opposite color, opposite sign, and they will cancel if they are equally populated. And if you look at the specific valley, and then you close the band gap and reopen it by changing the sign of your gated electric field, you are kind of swapping the conduction and valence band. You can also reverse the color of this band. So this is a material system that has flat band and tunable barrier curvatures, and that's what we need for the emergent phenomenon talked at the very beginning. And more specifically, when you have barrier curvature, you got this anomalous velocity, and you can experimentally pick up this anomalous velocity by measuring the Hall resistance, and you don't even need a magnetic field. Okay? This is so fundamental in condensed matter physics that every material, in principle, has this in it. Whether you have a finite anomalous Hall or not completely depends on whether the time reversal symmetry is broken or not, or in this case, whether the K and the K prime valley symmetry is broken or not. And usually when you have a time reversal symmetry breaking, you can also have the orbital magnetic moment due to the wave function self-rotation thing. And these are experimental signatures that we can use to detect the topological state. Okay? So the questions for experimentalists, how do you find such kind of stacking orders and keep it in your device? This is one way, and it's a way that we chose to do. Basically, again, this is a zooming in of that optical image. You see different contrasts here with the substrate. That's purely due to different number of layers. Well, if you use a different pair of eyes by using infrared light shining on this flake, and with the help of a little AFM tip to give you much better spatial resolution, you immediately realize there is internal structures in a region that seems to be homogeneous. Okay? The majority of this flake is 5-layer. And you couldn't tell the difference with optical eyes, but with infrared, you can tell there are bright and dark regions in there. And they correspond to the stacking order I was talking about. And you can confirm this by doing Raman spectroscopy, like Tony has shown us, that there is a subtle but very well-defined difference in the 2D peak of Bernal and the rhombohedral graphene that you can use to confirm, indeed, this is rhombohedral stacking. Okay? I am going to skip all the technical details of how to make the device and what is the yield of success, but if you manage to make one device that survives from all these things and stabilize this rhombohedral stacking order, you can do some DC transport, okay? You can assemble a stack that's composed of multi-layers of graphite, HBN, graphene, HBN, and you can use a graphite as a top and the bottom gate to control the charge density and the displacement field in the vertical direction. You make it into a Hall bar, so you can measure the longitudinal resistance and the transverse resistance as a function of temperature and magnetic field. So this is the simplest device that we have made. This is a 5-layer rhombohedral graphene sandwiched by HBN. There's no twist angle between layers of graphene. There's no moiré between graphene and HBN. There's no nothing. It's just part of graphite that nature gave us. And it shows already a very rich phase diagram when you tune the charge density and gate displacement field. And let me point out to you several things, okay? At the 0 charge density and 0 displacement field, you see this is a very insulating state. Well, this is already telling you the flat band correlation is already doing something there to the flat band, because with the large densive states that you see, you would expect a very good metal. But experiment, it tells you it's a very good insulator, so that it's already gapped out due to the flatness of the band. And when you dope charges into this material, you get all kinds of funny shapes, like a ring, some color difference across boundary, and this is something I would call as bubble. So all these are unexpected if you just take the single particle picture and feel a gap open the semiconductor. Okay, clearly something more complicated than that is going on. And these days, if you take a closer look, tell you that the spin or the value or combination of them is already broken due to the flatness of the band. I'm just going to focus on this bubble to give you an example, okay? So this, inside the bubble, you can also measure the anomalous Hall resistance at very low magnetic field. Okay, so the color outside the bubble tell you the normal Hall contribution at 0.5 Tesla, but clearly within the bubble there is much bigger value than the normal Hall, and this is the anomalous Hall due to the valley symmetry breaking and the accumulation of the anomalous Hall resistance.
Yeah, excuse me.
Yes.
Half Tesla. I don't understand this picture. So this lower corner, is the whole thing half a Tesla?
I'm sorry. So this triangle here is due to bad contact, so you should ignore that part. But this whole map is taken at 0.5 Tesla.
So what's anomalous about the Hall effect? You have a magnetic field on it.
Okay, so basically all what the magnetic field does is to stabilize it, because the Hall resistance can be positive or negative. If you keep it at strictly 0 magnetic field, it will fluctuate between positive and negative. And you'll get kind of random fluctuations here.
I hear you, but I'm asking a good question. If you have a half a Tesla field on there, which is pretty big, how do you know this Hall effect is anomalous?
Okay, so let's take a look at the hysteresis maybe, right? That makes it clear. There is a delay of flipping when you sweep the magnetic field back and forth. And if you look at strictly 0 magnetic field, there are two states. Both of them have finite RXY but the opposite sign. So this is anomalous Hall. Does that make sense?
This is going by me too fast. I don't understand what I'm seeing. So this is a plot of your sweeping B.
Yes.
And you have two. Which of those curves am I supposed to be looking at?
Okay, so I have 6 dots here parking a different combination of electric field and charge density. Right. And say I pick this blue dot, right? I fix the gate there and I sweep magnetic field, then I'm going to get this curve here, which is shifted vertically for clarity. Well, the important thing is when I sweep the magnetic field back and forth, I got a hysteresis in RXY. So this slope here corresponds to the normal Hall.
Is it about 0?
At the 0, yes.
So you have a half a Tesla field, but the Hall effect is switching side.
No. This is versus magnetic field. This is sweeping magnetic field back and forth.
Okay, fine.
Yeah. So this is just the magnetic hysteresis you get from any magnet. It's just in this case, it's orbital nature instead of spin. Okay, thanks. So, clearly time symmetry is already broken, right? You have anomalous Hall, you have magnetic hysteresis, and there are 4 states. As I mentioned, you can polarize in the K valley or the K prime valley, and in each valley, the magnetization could be pointing upward or downward or positive or negative. So a total of 4 states that you can manipulate there with magnetic field and the gate electric field. But if you forget about the details, all what you get here is sort of a magnet, and magnet has hysteresis, okay? Well, what's interesting that we found later is that there's a different type of hysteresis that you just scan the electric field and you measure the RxY, and you get, from left to right, from negative to positive, you get, red on the left and blue on the left. And when you sweep backward, most of this region got the color reverse, which means if you do a line cut here at fixed charge density, you are going to get this kind of what I call as butterfly hysteresis, which is clearly different from the magnetic hysteresis under sweeping of magnetic field. So what's going on here is that this is a different way of connecting the four symmetry breaking state. When you go from here to here, you're staying in the same valley, although the sign of the barrier curvature and the magnetization of this valley has already reversed due to the band close and reopen. The system decides to stay in that valley until you get out and jump back onto the other valley and persist through, so you get this kind of valley hysteresis. And the valley hysteresis coexists with the magnetic hysteresis. Both of them are orbital nature, so I give it a name as orbital multifluoricity. Forget about the name. What this really shows you is that now you have one knob, which is called electric field from the gate. You can control two things independently. You can go from here to here. You can control the sign of the magnetization, but keep it the same valley. Or you go from here to here. You keep the magnetization the same, but you switch the valley, which is another internal degree of freedom, just like spin. And this is more interesting than using multifluoric for controlling magnetism using the electric field, right? So this is just an example to show you that even in the most pristine form of 5-layer graphene in the rhombohedral stacking order, symmetry breaking can happen due to the flatness of the band, and there's experimental signatures like this.
Excuse me, in this experiment, is there any magnetic field applied?
There is a tiny magnetic field to prevent the random flipping.
How big is tiny?
Like 5 millitesla.
Okay.
So this is taken with probably like positive 5 millitesla. And the butterfly winds this way, okay? If you make it minus 5 millitesla, it's going to wind the opposite way. So there is a difference there. Anyway, so this is the simplest form, okay? Now I'm going to add more flavor to it. I'm going to introduce a transition metal dichalcogenide, which is known to have strong optical coupling. And the goal is to reach integer quantum anomalous Hall. Not only anomalous Hall, but make it quantized, okay? So as we said, there is anomalous Hall signal due to this time versus symmetry breaking and the sum of the barrier curvature. And in some sense, the Haldane model is kind of like a smart way of manipulating this barrier curvatures through the whole Brownian zone and give you integer quantum anomalous Hall effect means happening at the zero magnetic field. Okay, you don't need magnetic field here. And later, experimentally, it was shown in several material systems. In magnetic doped Ti, you got the Chern number equals 1 quantum anomalous Hall. The Hall resistance is h over e squared. And you can also get it in more intrinsic magnetic Ti. You get it in Moiré superlattice composed of graphene and TMDs. Okay, they all have Chern number equals 1. You just think of it as one channel that's kind of winding around the edge of your sample. What we did is that we put this 5-layer rhombohedral graphene on a WS2 layer, which has strong spin optic coupling. And it can sort of land some of those icing spin optic coupling to the neighboring graphene layers. And we do the same trick of applying top and bottom gate voltage. Eventually, we found at the charge neutrality of this device in certain range of displacement field, we can observe quantum anomalous Hall effect with a Chern number equals 5. Okay, if you look at this hysteresis, the RxY is quantized as h over 5e squared, which means there are 5 channels winding around the edge. And the 5 simply comes from the fact that I have 5 layers, and the pseudo-spin winding number is 5 times faster than in monolayer graphene. 5 pi per valley per spin. Okay? So this happens at charge neutrality, and phenomenologically, it's very different from what people have shown in other material systems. In the magnetic TI system, you have magnetic elements there, you rely on the ordering of the spin there to break temperature symmetry, and clearly we don't have anything magnetic here. We just have carbon, tungsten and selenium, and sulfur. And it's also very different from the integer quantum Anomalous Hall you get from Moiré superlattice of 2D materials, okay? If you notice, here I purposely twist away from 0 degree between graphene and HBN, and I minimize the Moiré effect there, and we don't think this has anything to do with Moiré. And phenomenologically, the quantum Anomalous Hall you get from Moiré superlattice happened at not 0 charge density, but a density that's enough to fill one of the band that has Chern number in it. Well, what we have is quantum Anomalous Hall at charge neutrality, means the K and K prime value are equally populated. So the only way to get there is to borrow the idea from the Haldane model. You have K and K prime value, but they have opposite gap, so their Chern number will add up instead of canceling. Okay? So we have some idea of how this happened. It was not predicted by theory, but this is our understanding now. It has a lot to do what happens at 0 displacement field. If you remember, at 0 displacement field, 0 charge density, it's an insulator due to correlation in the flat band. And we think this state is the so-called layer antiferromagnetic state, which means the spin has a preference of which layer to reside in. Okay? In that ground state, spin up electrons in both K and K prime valley are on the top layer, and spin down electrons in these two valleys are at the opposite layers. It just happened to be like that as a ground state. And then you can tune the displacement field to make transitions to other phases. Okay? So this is how it works. It's a little bit busy. Please stay with me. Okay? So when you are in the layer antiferromagnetic state, the 4 copies of spin in the valley orders are all gapped out. That's how you can get an insulator. But they are gapped out in different ways. Okay? For the spin up bands, the occupied state is in the top layer. That's what T means. Okay? And for spin down bands, the occupied states are in the bottom layers. They have, spin degeneracy and valley degeneracy. The two value will cancel each other. They have opposite barrier curvature, Chern number, and they will cancel each other. That's how it's topologically trivial. Now, the first thing you do is to apply some displacement field. What that does is to introduce an electrostatic potential energy difference between the top and bottom layers. Okay? You lower all the bands that's labeled as T. You shift them up in energy, and you lower the energy of all the bands that's labeled as B. Okay? In this case, you already break the spin degeneracy, because now if you cut here, you only have spin up band, not spin down electrons. Okay, then the degeneracy is reduced from 4 to 2. You can forget about these two bands. That's large gap and doesn't really matter for the topology of the ground state. And then you can further break the degeneracy between K and K prime corresponding to the same spin by introducing the Ising spin-orbital coupling. It will change, this term will change sign when you flip spin, or you flip the value. Well, in this case, K and K prime will break the degeneracy by, the valence band will have a difference in energy when you introduce the spin-orbital coupling from WS2. And then you have all the degeneracy lifted, you fine-tune the displacement field a little bit, you can close and reopen this band and change the sign of its Chern number. Now you have exactly what Haldane gave you, that the K and the K prime value no longer cancel each other, they add up to give you a Chern number of 5. This is our picture now, and I think phenomenologically it agrees pretty well with the experiment. Not only the quantization part, but all how this phase, transition happened.
I got a question now. I'm not following this. It's a whole bunch of words and no equations, but there's an idea
Yes.
that the spin orbit coupling is being borrowed from the surface layer.
Yes.
Is it big enough? Is it big enough? That's a reasonable theory?
So theoretically, we know that's on the, okay, I guess there's an experiment to verify that. Spin orbit coupling borrowed from WS2 is on the order of 1 to 2 millieV. And
how does one know this?
you can measure the band splitting due to spin orbit coupling by doing quantum oscillation measurement. Okay, you can have two bands that's degenerate to quantum oscillation. It gives you one period. But if you introduce spin orbit coupling, the Fermi surface in these two bands are, slightly different.
Yeah, I'm sorry. What I'm getting a little lost here is that you've got a 5-layer stack here.
Yes.
And the spin orbit coupling is way up here.
Yes.
And you need electrons to tunnel in there, borrow it, and then come back.
No. You only need to affect the electron in the top layer. That's why only the top layer bands are shifted, while the bottom layer bands are not shifted. All what matters is the difference between these two bands instead of like whether they both shift or not. Okay, so influencing just the top layer is enough in this picture. Okay? Okay, anyway, so this is how we think you can get a quantum anomalous Hall, quantized anomalous Hall resistance at 0 megafield and correspond to a large Chern number of 5. And remember, there's no twist between the layers, there's no Moiré effect. It's still pretty much just the crystalline graphene plus some spin orbit coupling borrowed from the neighboring layer. Okay? And next, I'm going to make this more exotic. Now, I'm not happy with just the integer. I'm going to make a fraction. And I need a different setting. So let's, briefly review this, although, the experts in the audience know much better than I do on this topic. But experimentally, it was observed in some very high quality two-dimensional electron gas system that magnetic field not only give you the flat band and the integer quantum Hall effect, but it allows the interaction effect between electrons to, dominate, and that can open up gap at the fractional filling factors. You get plateaus of the Hall resistance, not only correspond to the integer value, but fractional value, and you get dips in the longitudinal resistance correspondingly. Okay? And if you have such kind of ground state, it gives you a lot of interesting physics like fractional charge, fractional statistics, composite fermions, a quasi-particle. And as we have seen, you sort of can realize topology or the integer quantum Hall effect without using magnetic field, just by using the barrier curvature. Well, then people start to think about how can you do that for the fractional version of the quantum Hall. And indeed, there were, a lot of thinkings by theorists, not specifically any material system, but in general, just to think about what does it take to get a fractional quantum Hall, effect, or the state is called fractional Chern insulator, right? Just corresponding to the integer Chern insulator at the 0 magnetic field. And my understanding is, from this is you pretty much want to just mimic lambda levels. Okay, you succeeded once in lambda levels, and now you just want to mimic it without getting involved in magnetic field. So lambda levels are flat because you want the correlation, the interaction effect dominant. Okay, you want to quench the kinetic energy. So let's get some flat band in crystals without using magnetic field. Let's say we're smart in designing the crystal so the band looks flat. Second thing is lambda levels has Chern number in it. Okay, so let's again figure out a way to make the barrier curvature in such a way that this flat band has a Chern number in it. Okay, that's the second thing. And third thing is lambda levels are well separated by the cyclotron energy, so we can consider what happens within each lambda level when we partially fill it without worrying about how it talks to the other bands. And the analog of that in this 0 magnetic field version is that, okay, let's borrow some exchange energy that break the degeneracy between this band that has Chern number +1 and the band that has Chern number -1. Then we partially fill it. Maybe we got gap open at fractional fillings. Okay? Phenomenologically, just to mimic lambda levels. And this is, you know, the general ideas. And, you know, why would we want Moiré to help this? Okay? One way to think about it is that Moiré will make the condition of realizing this, you know, mimicking the lambda levels approach more easy to do in real materials. Okay? Since we talk about the band dispersion of E to the K to the nth order, let's start from here. Well, this doesn't look like an isolated flat band at all, right? Well, the first thing you can do is to put it on Moiré, say graphene on HBN Moiré. Then you can use the Moiré potential to open up a gap at the mini-Brillouin zone defined by the periodicity of the Moiré. Well, then you sort of cut out a flat part of it, but then maybe it's still not flat enough and it's still entangled with the conduction band. The next thing you can do is to open up a gap by using the gate electric field. Now, does this band look like a lambda level? Well, somewhat, right? Somewhat flat, and you know there's big barrier curvature around the band edge. So this also has Chern number in it. So maybe this looks reasonably like a lambda level. And why this is easier to do than in the crystalline form is, well, it's really hard to get a crystal that is flat in the whole momentum space. That's a lot of charge densities. And there are crystals that give you that, but that crystal, you know, so far hasn't shown fraction. But the Moiré help you simplifying the problem of, instead of requiring everywhere in momentum space to be flat, Moiré can cut out the flat portion of the band. You can still have very dispersive band at the higher energies, but all what you need is a small range of momentum space that is flat enough. And that corresponds to a much smaller charge density that's much easier to control, especially with gate. This has been the idea that theorists borrow and how they, you know, propose what the material can show this fractional quantum anomalous Hall effect. Okay, it was first predicted in twisted TMD material, twisted MOT2, twisted WSE2, and later experimentally it was indeed observed by transport measurement that you can have fractional, you know, quantized Hall resistance at the zero magnetic field in these two works. And there were also theoretical prediction in getting this in twisted bilayer graphene or some kind of strained graphene. But so far, the best experiment is to, you know, show the fractional Chern insulator at about 6 Tesla, which is still far away from 0 Tesla. Okay? The question is, can you get fractional quantum anomalous Hall effect in graphene? And that is when we start to, you know, think about this, and we already know there is flat band in 5-layer rhombohedral graphene, and the correlation topology could happen. So we decided to give it a try by putting this 5-layer graphene onto a Moiré superlattice with a neighboring HBN. It has a period of roughly 12 nanometers, corresponding to twist angle of 0.7 degree.
Excuse me.
Yes?
Moiré is coming from the HBN?
Moiré is coming from the spatial beating between graphene and the HBN.
Yeah.
Yes. And, you know, again, you can, you know, control these electrons by applying the gate electric field, right? So there are two things you can do. One is to apply a displacement field, open up the gap, and then you can push all these electrons to the layer that's part of the Moiré, okay, or next to the Moiré. So if you put the electrons in this very flat band right next to Moiré, what you get is not fractional state, but you get this insulating state at integer fitting factor of the Moiré superlattice. This is similar to what happens in twisted bilayer graphene. And when you reverse the sign of the displacement field and push these electrons away from the Moiré, you put them in this layer, that is 5 layers carbon out, you know, from the Moiré superlattice, something interesting happens if you keep increasing the displacement field, okay? Not yet at 0.4, 0.5 volt per nanometer, but something really intriguing happens at the level of 1 volt per nanometer. This is RxX, this is RxY, both taken at close to zero magnetic field, symmetrized, anti-symmetrized. And you see there is a region that's taking like a tilted stripe shape in the ND phase diagram. Overall tilted this way. And half of it at the lower density part looks like really, really insulating. It's so insulating that there's no current flowing through, and you cannot really measure the RxY reliability. That's why it's all fluctuating here. At the higher filling factor of the Moiré or density, you got this region that has clearly well-defined anomalous Hall signal. And there are finer features inside this region corresponding to integer filling of the Moiré, right? 1 electron per Moiré, 2/3, 3/5, 2/5. Some of them are easier to see in the RxY map, some are easier to see in the RxX map. Okay? And clearly, the message you learn from here is that there is a topological flat band. Okay? No matter if this insulating, we suspect it to be within a crystal, or this spontaneous temperature symmetry breaking, you need flat band. Now let's take a closer look at these states. Okay? First, let's look at the integer one. Integer one has Rxy quantized as h/e squared, and the Rxx go to 0 really well within a few ohm level, noise level, and it can persist to about 2 Kelvin in temperature. So this is as good as we expect from any quantum Anomalous Hall, even quantum Hall effect, but this is happening at 0 megafield.
This is the best one, right?
Yes.
Yours is the best one. You've got the best plateau of anybody.
Well, no, I'm saying this looks like what quantum Hall looks like, yeah. Right? I'm not claiming this is more precise in terms of quantization, no.
The point is, okay, fine, good.
Yeah. Okay, so this is the integer one. Everything looks good. This is a cut through that map to reveal those fractional states. Okay, you have 1, 2, 3, 4, 5, 6 fractional states that has Rxy, sort of quantized at the value you expect from that filling factor. It's 1 over the filling factor. And then you have dips corresponding to those plateaus in Rxx. The dips are not vanishing yet. It doesn't go to 0 yet. We think this may just be due to the electronic temperature is not low enough. That's what we know at this point. All these fractional states are in the so-called Jane sequence. They are odd denominators. And they persist to about 400, 500 millikelvin. And there's, at half filling, there's no plateau, there's no dip in Rxx. Well, the value is like 2h/e squared, or it's not quantized. And it varies linearly with the charge density. So it looks like composite Fermi liquid. There's no direct evidence yet. Okay? Phenomenologically, we got the integer, we got the fraction. And now let me tell you what are the puzzles here. This is not a done deal. Number one thing, we talk about how you can get this in Moiré, but the question is, remember, when we see this effect, the electrons are far away from the Moiré. So how do they even know there is a Moiré there, and how does the Moiré potential, kick in? Second is, even if you think there is a way these electrons feel the weak Moiré potential, if you really put the size of the Moiré mini-boron zone on the map, you can find that this flat part of the band is really, really big, which means even if you fold them into the mini-boron zone, you don't get isolated lambda levels. You get several mini Moiré band that are all entangled in the same energy range, and that just doesn't look like lambda levels. Okay? So this has triggered a lot of thinking in what's really going on here, and possibly explain why theorists has missed this particular system for fractional quantum Anomalous Hall effect. There are more puzzles if you compare to the other material system, twisted MOT2, where people also observe fractional quantum Anomalous Hall effect. There, it was initiated by theorists saying, there's some spin-optical coupling, and there's layer pseudospin. The pseudospin form kind of a skyrmion pattern in real space. There's some emergent magnetic field. If you think about this spin-optical coupling in such a pattern, well, the question is, none of this exists in the 5-layer graphene HBN system. So what is exactly the real important thing for realizing a fractional quantum Hall at the 0 magnetic field? Okay, these are open questions. And now, I probably should, speed up a little bit. Now let me tell you the new developments after those experiments, okay? The first thing is, we have at least 2 samples of 5-layer graphene that shows integer and fractions, so it's repeatable. Second thing is, we think it's not only specific to 5-layer graphene, although we start with 5-layer graphene, but this whole idea can also work with 4-layer, 6 layers. And there is an opportunity here, okay? Every lambda level has a Chern number 1 there, no matter if it's the first or the second lambda level. Well, topological flat band doesn't have that restriction. The Chern number can be any integer values. And indeed, this rhombohedral graphene system has witnessed a Chern insulator state with Chern number 2 in the ABC tri-layer graphene. And theoretically, it could have even higher Chern numbers in thicker layers. Well, experimentally, let me show you this. This is a whole doped 4-layer rhombohedral graphene HBM Moiré superlattice, okay? Now we're looking at the whole doped side. From the phase diagram, you see this is 1 hole per Moiré. It has vanishing RxX, has a big RxY. This corresponds to an integer quantum Anomalous Hall effect with Chern number equals 4 because the RxY is quantized at h/4 e². So indeed, there is a high Chern number topological flat band in this Moiré system. And there's another feature I want to draw your attention to. This is happening at around filling factor minus 2.5. It also has pretty small RxX and pretty big RxY. Okay, let's take a closer look there. If you look at the hysteresis, the RxY is almost quantized at h/3 e². And this may give you a feeling that this is a quantum Anomalous Hall with Chern number equals 3, right? And the RxX is way smaller than RxY. However, there's a puzzle right now that if you measure the Landau fan, you measure, this charge density dependence of the RxY and the RxX as a function of magnetic field, you expect to see the state shifts according to the Schroeder formula with a slope corresponding to 3. But what you actually got is something that has a much bigger slope than that. Okay? Phenomenologically, it feels like when you increase the magnetic field, the volume of this flat band increases, and you need to put 7 electrons in there, but only 3 of them contribute to the transport. This is something we don't understand, but I believe this is the first sort of like fractional fitting of a high Chern number, quantum Hall, topological flat band. Okay, question is why? And there's another opportunity that got opened up because people were thinking of engineering exotic quasi-particles, for example, parafermions, by putting superconductors next to a fractional quantum Anomalous Hall state, which is a very hard task because you need a strong magnetic field to give you fractional quantum Hall. At the same time, superconductors are killed by a magnetic field. Well, now you can sort of get the fractional quantum Hall physics at the 0 magnetic field and make it happy to live together with superconductor. And experimentally, we know there is superconductor in such kind of a rhombohedral graphene. This is not exactly 5-layer. This is ABC tri-layer graphene. There's some spin-off coupling, but there are superconducting states that we can observe, and maybe we can look deeper into it and make some kind of complicated structure in the same flake of graphene without borrowing another material. Because the problem when you bridge 2 different materials, the question is, do they get along with each other or not? This is a nice platform. You have very different physics that can be gate-tuned in the same flake. Okay, so this is my summary slide. We think this is a nice system that we should look further into for various reasons. Okay, there are fractional, Chern insulator, fractional quantum Anomalous Hall, and there are things we wish to do in the near future. There are also like correlated insulators. And there could be, interesting superconductivity here. And one of the theory, explanation of how we can get the fraction and integer quantum Anomalous Hall when the electrons are far away from the Moiré is that what we're really getting is an Anomalous Hall crystal, which breaks time versus symmetry and the transition symmetry at the same time. We don't know if it's there or not. And the last thing is, if we have flat band in a single flake that is rhombohedral stacking, we can possibly build more complicated structures, maybe by two of such kind of layers separated by a thin barrier like HBN, and let the electron and the hole in these two layers to talk to each other and form excitons. I remember Feng Wang was talking about this like maybe a couple weeks ago. We think this is a nice system to explore that type of bosonic physics here. Okay, with this, I'd like to thank you for your attention.
Thank you for a great talk. We had some questions during the talk, but still some time for additional questions.
Yeah.
Yes, thank you for the talk. So you mentioned, I believe, that you have more pentallayer samples that are showing the fractional signals.
Yes.
Is the RXX in those fractional signals similar to what you reported already, or is that different from?
Yeah. So now it's a valid question. It's on the order of like few kiloohm level. So as I said, we are not reaching the lowest electronic temperature yet. Previously, we just couldn't get any superconductivity in any graphene sample. Now, we can at least get superconductivity in some of them. I think the electronic temperature is now probably 1 order of magnitude lower than before. So we should recheck this in both samples and see if the dip gets deeper or even close to 0.
But I guess, but is the other sample showing
similar
or not?
Yeah, it's similar to this value.
Thank you.
Yeah.
Well, thanks for such an exciting talk. I just had a small question or suggestion. With respect to the origin of this Moiré effect when the electrons were not nearby, the kind of obvious possibility would be strain, which could propagate through the structure pretty effectively. Do you think that's playing a role?
Well, I don't think that's no, because this graphene itself is hard to make, and if you want to make a flake that you can access it with STM, clean interface, that's probably hard. I agree, that could be what's going on, but still, even if you have a very weak Moiré potential there, this whole range is so flat, and you fold it, you don't get obviously isolated lambda level. That's the more confusing part. Yeah. Yes.
The cases of this anomalous quantum Hall effect in graphene integers that I know about require spin polarization. There's an exchange, there are exchange effects going on, so my question is this: in your 5-layer sample, let's go to the 1 plateau.
Okay.
What happens if you put a B field in the plane?
Okay.
So as to point all the spins that way? Do you still have the effect?
It does persist. So there is experimental evidence that the spin is polarized, and you can even get, I think there's some magnetic hysteresis with in-plane field in the neighboring area on the phase diagram. Exactly in that state, did I apply in-plane magnetic field, explore that? We have not. But we borrow some other experiment other people did.
The reason I ask, is that the lack of spin-orbit coupling in this material is especially important. And the way you so that's what tells you that the magnetism is orbital. Okay, but in order to really make the case, you have to show for sure that spin-orbit coupling is not involved. I mean, we know it theoretically, but and the way to absolutely make sure of that is you point any spins around in the plane, and then if you still see an orbital, still see anomalous quantum Hall effect, it means that it's entirely in the orbits.
Okay, that makes sense.
That's the reason I asked.
That makes sense. We haven't done that. Yeah. Yes.
Does the other device that also shows the fractional states, does it have the insulating region at lower filling factors?
Yes. That big insulating region show up in 4-layer, 6-layer, and the 2 5-layer samples. That is a very robust feature.
And for the other numbers of layers, you haven't definitively seen fractional states yet, but is there still kind of like a diagonal window in ND space?
That's right. So if you look at the RXX, there's a dip at 2/3 fitting in both 4 layer and 6 layers. And phenomenologically, that insulating range is taking a bigger proportion of that stripe. And that eats some of those fractions.
I see.
So 5 layers somehow is still the best if you want to get the most fractional state out of it.
Thank you.
At least the sample we have down, there could be variations due to the twisted angle difference and things. We haven't got enough device to map that out. Yes.
You suggested that the finite resistivity is a finite temperature effect.
Mm-hmm.
Do you at least know what the temperature dependence of the resistivity is? The resistivity dropping with decreasing temperature?
Yeah, so I think it plateaus at a reading temperature of something like 300 millikelvin. Maybe that's the electronic temperature. From 300 millikelvin to 1 Kelvin, the RXX value in the steps will increase. And 1 Kelvin,
300 to 1 Kelvin
yes.
increases. Okay.
And 1 Kelvin is roughly where you lose the time versus symmetry breaking, and the anomalous Hall is just gone. Yeah. So I'm not particularly bothered by the fact it's not touching 0 yet.
Last question.
Yes.
So in the 5-layer plus unaligned HBN on both ends, there's no integer quantum Hall. Is that right?
For the
5-layer plus unaligned HBN on both ends.
Okay, yeah, so we do have sample that doesn't have Moiré with HBN, and we don't have a conclusion yet, but so far there's no integer or fractional quantum anomalous Hall at the temperature we have examined it. Whether they will show up at the even lower temperature, I don't know.
All right, so let's thank Long Xu again.
Yeah.